Hello everyone, my name is Astrid Vanneste. I am a PhD student at IDLab, part of the University of Antwerp and IMEC. Today I will be presenting the work of me and my colleagues on discretization methods for communication learning using multi-agent reinforcement learning. What we do in communication learning is that along with learning an action policy, each of the agents within our system also learns a communication policy. This communication policy is used by the agents to share information with each other and to discuss any possible strategies to achieve the goal. The most common approach to learn to communicate is communication learning through backpropagation. And what we do here is we correct the communication policy of the sending agent by using the gradients that come from training the action policy of the receiving agent. So basically we assume that both of these policies are part of one big network that has the observation of agent 1 at time step t and the observation of agent 2 at time step t plus 1 as inputs. However, when we want to use discrete communication, which allows for smaller messages and is more similar to human language, we have to apply special discretization methods to keep the communication channel differentiable. This is essential if we want to use communication learning with backpropagation. In the state of the art, multiple of these discretization methods have been proposed. However, we cannot compare them since they are applied on different communication learning architectures, and these works use different environments to evaluate their methods. Therefore, in our work, we present a clear comparison of multiple discretization methods, and we evaluate them on several environments to give a clear view as to which discretization methods you should use. We will apply these discretization methods on the dial method presented by Forster. And this dial method is very similar to what I explained before. So on this figure, there are two agents displayed across two different time steps. Now, if we follow agent 1, it will use its observation to generate a message, which will then be discretized by the discretization unit, which will be filled in with one of the discretization methods I will discuss later. Here we will receive a discrete message, which will be transmitted to agent 2. Agent 2 will combine this information with its own observation to generate an action. This will result in a reward, which will then be used to correct both the action policy of agent 2 and the communication policy of agent 1. Now we can look at all of the different discretization methods that we will compare in our experiments. First discretization method that we will look at is the discretize regularize unit, or the DRU. This was proposed along with the dial method by Forster. The DRU has two separate modes. One is used for training and one is used for execution. During execution, we no longer need a differentiable communication channel because we no longer train our networks, and therefore we can just use straightforward discretization. During training, however, we do need differentiable communication channel. And what we do then is we allow the agents to communicate using continuous values. However, we want these continuous values to be easily discretizable during execution. And what we do to encourage this is we apply some Gaussian noise to the message and then apply a sigmoid function. When we look at the sigmoid function, what we want the agent to do is to generate values that will result in either a 0 or a 1. And when we see what the impact of the noise would be for these extreme values, we see that the impact is quite small, while if the agent would produce values somewhere in the middle, the impact of the noise would be a lot bigger. And therefore, the agents will encourage to produce these extreme values, which are easily discretizable. The second discretization method that we will look at is a straight-through estimator. This one also has two separate modes, which are used for the forward pass and the backwards pass, instead of for training and execution. During the forward pass, We will discretize the inputs by applying a threshold function. However, during the backwards pass, we will not use the gradients of the threshold function, but we will apply the gradients of an identity function. The benefit of this is that during training, the inputs will already be discretized, which allows the receiving agents to start learning how to interpret discrete messages, while we still have a differentiable communication channel. The next method is the Gumbel softmax. The Gumbel softmax starts by applying the Gumbel max trick. This allows us to sample uniformly from a categorical distribution by applying Gumbel noise. Here we use the argmax function, which is still not differentiable. And therefore, in Gumbel softmax, we replace it with a softmax function. This will result in an approximation of a regular sample, but it will still result in a differentiable communication channel. The next method is a novel method that we present ourselves in our paper, which is called the straight-through DRU. Here we apply the principles of both the DRU and the straight-through estimator and combine them. So we have in the forward pass during training, we apply a threshold function with Gaussian noise added, and during evaluation, we don't add a noise. And during the backwards pass, we use the gradients of the DRU. Last method that we will look at is the straight-through Gumbel softmax. This one has not been applied to communication learning before, but it has been applied in other areas. So in the forward pass, we apply sampling using the argmax, and in the backwards pass, we use the gradients of the Gumbel softmax, using the softmax instead of the argmax. Now we can take a look at the results. The first environment that we will test is the matrix environment. Here we have a set of agents that all receive a certain number in a certain range. After communication, the agents have to indicate whether or not all the agents receive the same number or not. In our experiment, we use a scenario where we have 5 agents and 256 possible labels. To represent these 256 labels, we will use 8-bit messages. When we look at the results of this experiment, we can see the following things. So what you see here is a graph which represents the mean return in function of the training iteration. So the evolution of the return throughout training. And the first thing we can clearly see on this graph is that the straight-through estimator clearly outperforms all of the other methods. It learns extremely fast and also reaches a higher reward than the other methods. What we can also see is that the straight-through variants of the Gumbel softmax and the DRU outperform the non-straight-through variants. To explain the fast training time of the straight-through estimator, we take a look at the communication amplitude. This indicates the average absolute value at the input of the discretization unit. And when we take a look at the graph on the right, which shows the communication amplitude in function of the training iterations, we see a clear difference between the straight-through estimator and the other methods. Each of the other methods has a communication amplitude that rises significantly more than the communication amplitude of the straight-through estimator. This can be explained by the noise that is included in each of these methods to encourage discretizable behavior. This noise is not included in the straight-through estimator, and therefore the agent is not encouraged to produce such extreme values. When you put the graphs of the mean return and the communication amplitude on top of each other, we can see that there's a clear correlation between when the communication amplitude starts rising and when the mean return starts rising. And this is not the case for the straight-through estimator agents. And this shows that for each of the methods except for the straight-through estimator, a certain communication amplitude is needed before the communication is interpretable by the receiving agent. And this causes a delay in the training performance, which causes a slower training speed for all of the methods except for the straight-through estimator. The next environment that we will look at is the speaker-listener environment. In this environment, we have two agents, the speaker agent and the listener agent. The speaker agent will observe which of the three landmarks is a target landmark, and it then has to communicate this information to the listener. The listener will interpret this message and then has to navigate towards the target landmark. When we look at the results in the speaker-listener environment, we can see that the straight-through estimator doesn't perform as well as we saw before. So in this environment, it performs the worst across all of the methods that we tested. And the Gumbel softmax, the DRU, and the straight-through Gumbel softmax perform the best. In our last experiment, we used the same matrix environment as we used before, this time with 10 agents and 2 labels. The only change is that when agents communicate with each other, there is a 50% chance that one of the communication bits will be flipped. So in this case, the agents have to pick a communication protocol where they can account for these errors and can actually still understand the message. In the results, we can see that each of the methods, except for the straight-through estimator, is able to find a correct communication protocol in this case. Our hypothesis is that the noise that is part of all of these methods, except for the straight-through estimator, actually helps in finding a robust communication protocol that is able to deal with these kinds of errors. We can see how the agents are able to deal with these kinds of errors when we look at the communication protocol in more detail. So what you can see right here is the communication protocol before errors are applied and after errors are applied. So what you see here is on the y-axis, you can see the two possible input labels, 0 and 1. And on the x-axis, you can see each of the possible messages using 3 communication bits. Here we can already see a big difference between the straight-through estimator and the other methods. The straight-through estimator represents both of the input labels using the same message. And this of course means that the receiving agent isn't able to determine which label the other agent got, and therefore isn't able to correctly choose an action. The other methods, however, were able to learn a communication protocol where we have a distinct message for each of the input labels. And in addition, after we apply errors, where we flip one of the bits of the messages, we can see that the possible messages after errors are applied still are separable between the two different labels. So a certain message still only responds to one possible input label of the other agents, which means that even though errors occur, the receiving agents are still able to determine what label the sender got. So to conclude, we presented an analysis of different discretization methods when using communication learning through backpropagation. We applied those different methods to several different environments. Within these different discretization methods, the straight-through Gumbel softmax hadn't been applied to communication learning before, and we also introduced a new discretization method, namely the straight-through DRU. In our results, we saw that in general, the straight-through DRU, the regular DRU, and the straight-through Gumbel softmax provide the most consistent results. So in all of the tested environments, these methods were able to achieve the objective, while the straight-through estimator and the Gumbel softmax were not. However, in specific cases, the straight-through estimator can still result in a better performance. Like we saw in the matrix environment, it had incredibly fast training when compared to the other methods. However, in the error correction task, we saw that the straight-through estimator fails completely. So this was all for my presentation. Thank you for watching, and I hope you enjoyed it.